Humans observing this video are immediately able to perceive and understand the pose of the portrait person. The goal of this work is to train an algorithm that can automatically infer the full three-dimensional body configuration of a person in an image or video, both indoor and outdoor, with unconventional poses, varied backgrounds, and a multitude of camera viewpoints and scales. Typical supervised methods require a large collection of input images and paired annotations. While this can be easily accomplished for 2D key points on the image plane, obtaining such supervision for the 3D pose of a person is very expensive, time-consuming, and prone to error. At the same time, there is a large quantity of image datasets annotated with 2D landmarks of the human body, with a large variability of the portrait poses, actions, scenarios, and viewpoints. The main contribution of our work is a methodology to leverage 2D keypoint datasets for the task of 3D pose estimation by using relative depth labels between a sparse set of keypoint pairs. We collect ordinal labels for our task in the following way. Given a picture of a person and a pair of 2D keypoints, we collect depth information by asking which one is closest to the camera taking the picture. This type of data can be easily obtained by annotators on existing 2D images. To find out if humans can provide high-quality annotations for relative depth, we evaluated annotator performance on Human 3.6M, which is a mocap dataset containing ground truth 3D information. We selected a subset of 1,000 images and collected 5 random keypoint pairs and had them each annotated by 5 people. We can see the performance curve of annotator accuracy against the relative distance between a pair of keypoints along the depth dimension. Annotator accuracy is close to random guessing for a pair of joints located at approximately the same distance from the camera, and grows to around 90% when the distance is 20 centimeters, as seen in yellow. The relative order of pairs that are more than 40 centimeters apart from each other is always identified correctly. We propose an algorithm that can be trained without any 3D data supervision. To do so, we introduce a novel loss composed of 4 terms based only on 2D information and relative depth labels. The ranking loss is defined to maximize the distance along the depth, or Z, dimension for a pair of keypoints that have been annotated to be in a specific relative order. The previous loss only constrains the Z dimension of the predicted outputs. So we use a reprojection loss to constrain the poses also along the X and Y dimensions. Given an image with its available 2D ground truth skeleton, we obtain a 3D pose prediction by our network and measure the reprojection loss by using a projection matrix under the assumption of a scaled orthographic projection, with the scale parameter S predicted by the network. The loss is measured as a Euclidean distance between the predicted and ground truth 2D skeletons on the image plane. We add a skeleton loss that takes advantage of pose priors such as known ratios and symmetries of the human body. Given a pair of joints which have length of a certain known ratio in 3D, we penalize the corresponding joints in our prediction if they don't respect the same ratio. We design a root loss to address the ambiguity between scale and distance when projecting a scene onto the 2D image plane. This forces our network to center all the predicted skeletons in the origin, leaving scale as the only ambiguous quantity. We conducted experiments on the Human 3.6M dataset and compare the performance of training a state-of-the-art architecture with full 3D supervision versus our approach that uses only relative depth labels. With ground truth input 2D key points, the average error over the test set is higher by a distance on the order of 1 centimeter. If instead the inputs are detected 2D key points, both methods perform slightly worse, and the gap grows but still remains less than 2.5 centimeters. We also report the results of a recent method which uses relative depth annotations in conjunction with 3D pose ground truth. Qualitative results testify the high performance of our method, shown on the right, compared to the supervised baseline. Our training methodology is the first that allows to train a network for 3D pose estimation on large 2D image datasets without requiring any 3D ground truth. We collected relative depth supervision for the entire Leeds sports poses dataset. On the LSP Relative Dataset, the ground truth 3D pose is not available, so we measure the error in terms of percentage of incorrect relative labels predicted for an output pose and compare to the supervised baseline. Both methods, pre-trained on human 3.6M, obtain an average error of 34%. However, after fine-tuning our method, we reduce the error by more than 10%. We hypothesize that this is due to the presence of the reprojection loss, which is able to account for very unconventional poses present in LSP and not in the original human 3.6M dataset. We observe how the predicted output poses are significantly improved in terms of their reprojection on the image plane in the following qualitative examples. In summary, we developed an algorithm for 3D human pose estimation using only relative depth labels, and showed that they can be used to train a network with comparable performance to 3D supervised state-of-the-art. The main paper, containing an extended discussion of our results and our code and data, can be downloaded from the above GitHub link.